Thank you very much. Okay, let's start with this one then, so you can have some time scanning that. It's what they slide afterwards. I'm not sure if I'm gonna. I usually run over, unfortunately, so hopefully we get some time for questions. We'll see. All right, I'll start with actually a confession. I've been doing this, not talking, but doing IT for 20 plus years. And in the later years, I've been doing some talks here and there, and I've sort of come into the idea that I have been around so long that probably somebody are interested in listening to me, so I present what I've done before. And by that, I sort of end up running into the mechanism of things, right? I don't know who went to the first talk here on this stage, but about the Dreyfus model, that you end up presenting things that people can follow. And the thing is that that's very mechanistic. It's very process-driven, right? So you should just do this and then everything will be fine. And I've done that myself for a long time. But the last few years I looked into system thinking. And that sort of changed my perspective on things. I don't know who have looked into system thinking as a topic. A few. Because it's not, don't think of IT systems, if they have systems in them, but they're different. System thinking is about a way of framing things, a way of looking at things. And so by doing that, it has changed my perspective quite drastically. So a lot of stuff that I did before, I must admit that it wasn't that good of advice, actually. It's very reductionistic often. We'll come back to what that means later on. So when we do this stuff, we often look at the parts and try to optimize the parts without seeing the whole. That's basically what we often do. And I've done that through probably my whole career. So lately I've looked into system thinking, but specifically a brand of it called sociotechnical systems. Anyone heard of that? Oh, there's a few. Good. Then we have something. Sociotechnical system, as the name dictates, is about there is a system and you want to optimize both for the social and the technical. And the technical is not necessarily technology. Techne, it comes from the word techne. So it's about techniques, for example. So processes are part of the techne thing. So if we, and I feel we focus often too much on the techne thing. We like processes and we like technology. That's why we're in STEM, right? I come from STEM. So I have a serious deep dive into social technical system design, which comes from social sciences. Totally different a different branch of science where I've been before. I come from natural sciences. So that's why I picked this title. Because I think it sort of indicates that there's more to this than just the technical bits. That when we are developing things, it's really important to be good neighbors. And not good neighbors as this class needs to talk to that class. That's still technical, right? But the social part, the people doing the thing. Because we are inherently working in a social technical enterprise. We are writing code as people for other people to use. People writing code for people. So it's very social. So it's really odd that I haven't thought this before, really. And also that fits into Agile nicely. It's like, how do we collaborate? Just a little nerd snipe here, though. I still think Agile largely, as it is implemented, is anti-systemic. We're not going to talk about that today, unfortunately. So it's sort of a hint of maybe getting invited back again. But I really want to dig into that at some point. So this proverb, for me, sort of the association I get is these mossy stone fences. So they're fences, they're not walls. If you come from a more urban area, of course, that would be white picket fences. I moved from these type of fences to the town, and now I have a white picket fence, I must admit. And you probably can associate what's good with them and why you need them and all that stuff. It's like, what's my turf and what's yours? But it's not a wall. It's not like I'm blocking you out. We just agree on this is my thing and this is yours, and we can collaborate. We talk over the fence, for example. In a rural area, it's really important, for example, these ones, delineation between farms. But also keeping the livestock in and maybe the wild animals out. But it shouldn't be a blockage for anybody else. So in Norway, we have something called allemannsrett, which is basically freedom to roam. It's actually written in law. Anyone can go anywhere in Norway, in the outskirts, unless it's a real private property. You can go anywhere. So they shouldn't block you from moving between them. So I think it's important to see that these fences, they are permeable, if you like. So this is where I come back to what I talk about, this boundaries all the time. So many of my previous talks have been about modularisation. So this is why I'm going to take this fence, this image of a fence, when I'm thinking about modularisation. I want to bring a little quote from this guy, Buckminster Fuller, American system theorist, designer, and architect. He said, you have to remember that the boundary, you have to remember that any boundary is a useful fiction. Because we put these boundaries in for a reason, and they're not there to begin with. We design them in. And by doing that, we should be very conscious about why we put it there and for what purpose. Because they can both enable and they can constrain. Oh, sorry, they can limit you. So there's enabling constraint or limiting constraints. So what is an outer fence, for example, in a farm? And what is an inner fence? What's the fence that you use inside to keep your livestock away from your grain field, for example? Or what do you want to sort of delineate what's your area and the other ones is an area? So there are different ways of using them. Which also means that they are a model, and they're always flawed by design. There will never be a correct model. As Rebecca said earlier, there isn't a perfect architecture. It doesn't exist. You can't. And that's where the confession comes from. I think I had thought there was a perfect solution to everything. We just had to find it. It's out there somewhere. We just have to get the right people in the room, or I have to think about this enough, and then we can. Perfect. It's going to work. It isn't. Systemic thinking states there is no perfect solution. So we do, and even that it is not a perfect solution, but it can also be done so that it breaks the system. That's another interesting system thinking idea. Even if you optimize all the parts of a system, every part works perfectly on its own, it can break the whole system. That's another interesting aspect of system thinking. So if we sort of agree that modularity is a good idea, and it's really hard, why is it then still worth it? And we probably all know this, and there is a lot of talks about saying all the technical things, so I'm going to focus on the social things that are also advantageous of having boundaries, so good boundaries. Then. So let's start with some simple ones. And that is about you get the idea. We use it as a problem-solving tool. To deal with complexity, we like to box things in, right? We want to focus on this first and ignore the rest. We do that all the time. Again, that's what I've done most of my professional career. I focused on this class, on this model, and ignore the rest. Which is a natural way of coping with complexity, but it brings about a great deal of problems, as we will see later on. And also there is something here called a boundary judgment. You have to decide what boundary are you in. Who decides what is the system, for example? Or what is that part of that system? Who draws the boundary? So that was the first one, just a coping mechanism for complexity. Another one is also related to psychology. It's a cognitive load. For those of you who have read Team Topologies knows all about this, probably. So it's mainly about how you learn stuff. What helps you and what hinders you in learning new stuff. Quickly, just to mention some of them. The extreme cognitive load is like, just before I go into it, it's just a cognitive load. The idea is that there is a limitation to it. There is not an infinite amount. At some point, you're going to reach the limit and things are going to break. You do errors and stuff like that. So extraneous cognitive load is load that is not part of what you're looking into. You have to relate to it. When I did online talks, I used being online, doing talks online as an extraneous load for me as a speaker. I have to care about the network being up, for example. I shouldn't have to care about that. But I have to, because I'm doing online. So Team Topologies is really good focusing on this with the platform teams and then the subsystem team, even the enabling team, right? You want to lower the cognitive load of the teams. Team Topologies is excellent there. And then you have the germane cognitive load. That's also really interesting. It's about you want to map what you learn to what you already know, because that's easier for you. So we tend to maximize that. You can imagine that biases come into play here, for example. Or that just look just like that one, for example. When microservices come about, and I've done SOA before, I said, microservices, just like SOA. Of course it isn't. It's close, but it isn't. There's always a difference when it comes. So that's the sort of the way that our brain works, that we want to match things. And then there's the intrinsic cognitive load. That is sort of the load that's inherent in the problem domain you're into. And you can't, that's the thing that you have to sort of relate to. I mean, you can't get rid of that. But you can simplify it. And simplify it is a good, modularization is a good way to simplify it. Splitting thing up, getting a decent set of boundaries, so you can actually focus on some parts, relatively safely to other parts. A second one I mentioned is scaling organizations. If you're a little startup and you want to grow, the easiest way to grow is adding new teams, adding new components. Right? Instead of adding people to the team, you create new teams and you create new components for those teams. So that's a good way to do modularity. And also you want to reduce the coordination cost between these components. So you have to create the modules so that the teams that owns the modules have to coordinate as little as possible. Not zero. Again, back to system thinking. You would never have an autonomous team in a system thinking perspective. It doesn't make sense. Because a system consists by definition of parts, and the parts have to interact in order to be a system. If it's a part that's not connected to the rest, it's a different system. So it's inherently, it has to be connected. But you want to reduce that as much as possible. And also you want to make them as thin as possible. So there's as little as possible going across these. So you probably heard this, we need to communicate better. So you send people off to some psychology thing or team building thing. You need to communicate better. That's the problem. That's anti-systemic, because you look at the effect of something, not the cause of what was happening. Why are people communicating less? Or why is there a problem with the communication? Maybe they shouldn't be communicating at all. Maybe that's the problem. Like Jeff Bezos said, communication is terrible. That's the same idea. There are actually other interesting things when it comes to system thinking here and the way that teams are constructed. Is that if you see that, this team, they're so unmotivated, right? Or there's so much politics here. Or that team is controlling the other team. There's so much power play. All these stuff are actually systemic things that you look for. They are anti-systemic. When you see these things, your system is probably wrong, not the teams or the parts. System as a whole is built wrong. So again, back to bond relocation. Where do you draw that? And also for speed, not for typing faster or delivering things faster, but getting the waste out of the way. So you don't have to do all the coordination stuff because they are independent, it's semi-independent or semi-manageable, semi-autonomous, or whatever you want to call it. So you want to move fast. That's another one. You probably will have an idea where I'm going with this. Because since this is Agile meets architecture, it's really interesting to see that architecture can have a profound effect on your agility. If you have the bad architecture, it doesn't matter how agile you are. You're going to struggle. If you have to fight, if you have to wade in mud, it's going to be hard for you. This is from Foot and Yoder paper, the paper they have called The Big Ball of Mud. Sadly, architecture has been undervalued for so long that many engineers regard the life in the big ball of mud as normal. I've been there. I've actually been proud of the huge monolith that we were working in. We actually used it as a recruitment argument. Come and work for us. We have the biggest monolith in Norway. We have so many code lines you wouldn't believe. We actually listed the number of code lines. So at some point, actually in my career, I thought that was cool. That was a good thing. Again, I'm very, very anti-systemic. So modularization of architecture, I think, is essential to do. You can't be agile if you have to fight your architecture all the time. So loose coupling, high cohesion, all that. And there is also an interesting thing this is from Dr. Carlis Baldwin. She's an economist, really. But she's really into those options that you create with having modules. That actually modularization is the financial force. She actually said, a quote from her is that experimentation and recombination is the new game with IT. That you have parts, modules, you can recombine it and create new things. Yes, there are some reuse idea here, but still. So multiply, the fifth is the multiplication of options you have. So I think we sort of general idea that all this modularity thing is cool and we need it, and we even have data for it. This is from, of course, Accelerate book, the people behind the Dora metrics. There's a quote in there that's really caught my eye when I wrote it. Probably a bias again. But a loosely coupled, well-encapsulated architecture is the biggest contributor to the IT performance, even larger than test and deployment of automation. That's saying quite a lot from the people behind the Dora metrics on how to get stuff into production faster, continuous delivery and DevOps. Right? So they see the need, the importance of having a good modularized architecture. So we have tried this for ages. I mean, again, I'm not that old, but I've been through the J2EE, Java Enterprise Edition, and even some Corba before that, and some procedures even before that. So we had tried this, and now it's microservices, all the rage. So why is it still so hard? That's the question I have. And this is where system thinking comes in, at least from my perspective now, is that system thinking helped me understand why it's so hard. Because we're into complexity. And of course, some of you probably know Ken Evans, so I'm not going to go into that, but it's about system thinking again, complexity theory, basically. A good illustration here from a children party. I know Dave Snowden used that as an illustration. So how hard it is to... you can't have a plan for a birthday party with kids. You can have the sort of perfect plan before the kids arrive, but then it's all gone. It's like damage control after that. It's fun. It's nice, but it's a very different thing that you probably envisioned when you started the party. So we tend to think of things as linear. There's, of course, an effect to everything. And I think a good chunk of the reason why that is because most of us have STEM backgrounds. And in natural sciences, that is what you look for. Causation between things. But the world is a bit more non-linear than that. It's highly non-linear, actually. So we tend to create this little bubble where we have sort of think we have control, but it's an illusion of control. And I think we do that when modulars as well. It's at least a considerable danger when we do that. So let's just a little recap of what system thinking is. And for me, it's very simple. It's about parts and wholes. But although there's more to it than that. So you can view it as a set of relations within a boundary, for example. It doesn't have to be more complex than that. But when you really take it on board and look at things that are around you as systems, you figure out there's more to this. So, okay, we have parts, but what is the whole to this part? And when does the whole stop? When are you going to stop? When you say that, okay, this is the boundary of the system? Do you want to continue and say that this is part of that, and this part of that, and this part of that? And you end up with the universe in the end, right? So there has to be some judgment here going on. And also, in addition to that boundary critique, as they call it, there's also all this about multiple perspectives. And I think we'll use that a lot as well. I'm going to come back to that later on. But I use a system here as with a set of cogs. So one cog moves, everything moves, and the whole is different. Right? So that shows that there's a part, there's a whole, and everything is interconnected. Nothing here is separate from anything else. Everything is interconnected. But do you see a problem with this? Hopefully, we're going to get back to that later on. It's very mechanistic still. But it's a system. It's a machine model. Right? It's a way to view the system as a machine. So here also we assume there's predictability and there's a determinism. When we turn that wheel, we know what the other wheels are going to do here, in that model. So the whole is the sum of its parts here in this model. It's a system idea, but it's still one-to-one. It's fairly linear. But what happens then? If somebody decides, we want to change, we want to be different than the rest. What happens then? Actually, in this model, you've broken the system. Yes, that only new part looks brilliant. The other parts is going to struggle with this, and the whole system is degraded. So local optimization is the worst thing that can happen to our system. And that's what I think we have been doing a lot with, for example, Agile. We want to be super agile. The rest of the things, we don't think so. We're going to work as before. Or now we believe in the waterfall thing. We're going to work with projects still. No, we're going to be super agile. We're going to do Scrum and everything. Cool stuff. you see, that's going to create a problem for the whole system. Yeah. So some good quotes from some bigger system thinkers than I. This is from my famous one, Russell Lakoff. His definition of a system is really good. A system is never the sum of its parts, it's a product of the interactions. He also says that a system is more than the sum of its parts. It's an indivisible whole. It loses essential properties when it's taken apart. Again, as an introduction, I had a confession to make. What is the biggest tool? What's the main tool an architect uses to design a new system? Analysis. And what is analysis? Taking a system apart and looking at the parts in separation. That's analysis, by definition analysis. So then we are focused on the parts, not the whole. So Lakoff is saying this is actually basic reductionism then, right? You decompose, you explain the parts, and then by explaining the parts, you understand the whole. So, and that sounds like, yes, and isn't that how we do stuff? In science, of course it is. But we are actually not in doing science, to be honest, because we are a social-technical system, and it's different. So we need something, as Lakoff actually, of course, said that we have to move from what he calls a machine age into a system age. So we need something more. He's not saying that analysis is to get rid of. We need something in addition to analysis. We need synthesis. And synthesis means that we have to take one step up. If you're going to look into a system, you have to understand what is the system part of. And by understanding that, then you can dig back in. So you start putting things together, like in the future whole, explain the whole, and then deep down to understand the parts. Right? Understand the containing whole system, and then explain what the larger system is. So if you're going to build a car, you have to understand why you need a car, what the car is going to be used for, who's the demographics for it, la 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 la. What sort of regulations do it have? If you don't understand the containing whole, you're not going to be able to understand the part. It's because synthesis focuses on the function, so it explains why things are there are. Whereas analysis focuses on why things operate the way that they do. So one reason I think that's one of the bigger reasons I've seen for why modularity fails. It focuses too much on the parts. I've certainly done that. Another interesting quote is from this woman, which you probably know. For those of you who have gotten a little bit into system thinking, that's the name you encounter first. Thinking in system book is amazing. But I like this her definition of a quote here because it gives you another direction to what system is. A system, a set of interrelated elements organized to serve a particular function or to seek a particular goal. You remember that cog and wheel thing I had earlier? I didn't say anything about the purpose of that thing. Yes, it was interconnected, it was a whole, it was a little parts and whole and all that. But I didn't say what was the purpose of that system. And this is what Lakoff says as pulling up, seeing the whole. So if you look at what is the function or what is the purpose or the goal of a system, then things changes quite dramatically. Lakoff also looked into this quite a bit. So he actually went so far he defined different types of systems based on their purposefulness, based on the purposefulness of their parts or their whole. So you describe, okay, you have a system called a deterministic system. There you have the parts have no purpose and the whole has no purpose. Your car, for example, doesn't have a purpose. If you're not driving it just sits there. It doesn't want to go anywhere. At least I hope so. At some point there might be AI that might change that, but as of now, the car is a deterministic system. And what we build with our code are deterministic systems. So there is no purpose for the parts or the whole. And then they go, and this is a hierarchy of type of system. The next one is animated systems. Here the parts have a purpose. Now I have no purpose, but the whole has a purpose, like you and me. The parts of me, the heart, the lungs, doesn't have a purpose, but I as a human being have a purpose. Actually, Lakoff goes so far as saying we are open, purposeful systems. That's the definition he has of people. They're open purpose systems. There is something we want out of life. There's something we drive for. And also the purposes change all the time. That's another interesting thing. And then you have another level, it's the social systems. Here the parts, consisting of you and me and a team, we all have purposes, and the whole has a purpose. Because you have to assume that this is a social group that is put together or has been selected for itself to be something more than the parts. So a family or your teams, right? Again, very interesting because you have to align these purposes. If they go different ways, they're going to break apart probably at some point. And it also includes another level. It's the ecological system. We're not going to go into that too much, but there the parts have a purpose, but the whole doesn't necessarily have a purpose. Humankind, for example. You will encounter these systems as well. But what I find striking is that we almost always, when we design systems, IT systems, we think of them as deterministic. And we design them as such very often. But we are in a social system. That's what we really are. So can we sort of abstract away all that social part and believe that we can create systems that are deterministic? It's small shots of time maybe, but they change as we showed earlier. The parts change. So if you take in a social system, then the parts have people in them. And that changes modularity a lot. You remember that code that changed? People change all the time, from day to day, from hour to hour. Team change, people change, the parts change, the whole change. And the purpose of the team may change, the purpose of the people change. COVID hits, everything change, right? So that changes the play quite considerably. That's why I'm so almost obsessed with getting this across, that social part of a system, social part of a social technical system is so vital, and we ignore it mostly. So if you have the team, it's actually an open system even. I didn't go into the open system not too much, but the interesting thing is that the open system is exposed to its environment. So a team is not only exposed to the next teams that I work with. They are that, of course, true. But they also are exposed to the whole company, and also the extended technical fields and the social fields. You hear this, oh, you come to work, you have to put your private life at home. That's terribly reductionistic. Doesn't work. You are there as a whole person, and you have a purpose that you bring with yourself to your work. Yes, you try to align yourself with the purpose of the job that you're in, the team that you're in, but you still have a purpose on your own. And ignoring that has detrimental effects. That's what I've seen from social sciences. And they actually call this maladaptive. We do this all the time. This is not a talk about that, but again. So, if we want to do modularisation then, and this is so hard, what can we do to make it a better chance that we get it right? And I like this illustration of the idea of looking for seams. Michael Featherstone talked about natural seams in things, right? So these are geological formations, though. And also, I think Team Topologies also talked about sharing layers or something like that. Fracture planes, they call it. Same thing, same idea. These are actually fracture planes. So where's the discontinuity between things? Let's see if that can help us. The classical one is, of course, this. This is probably what we have done most of our lives. This is what David Panard suggested in 1972, so it goes back a bit. He said, we propose, this on the criteria of decomposing a system. He showed that there was one way, which was a workflow kind of way, and suggested another one instead, and this is what he suggested. We propose instead that one begins with a list of difficult design decisions, or design decisions which are likely to change. Each model is then designed to hide such decisions from others. Encapsulation, basically, right? Like a huge driver for what became object orientation later on. So this is what we mostly do, and also when I do modularisation thing, that's how we do it. We try to figure out if there's something here and there's something that, and also there are these change often, so we put them that in the same thing. Oh, these never change, so we put those in a big chunk over there. Utilities, right? So we have a very limited view on it. I think this, and also this is very emergent. You have to go at it until you discover what a good module to be. So it's very bottom up. And I loved what Rebecca talked about earlier today, about architecture being emergent. That is, for me, that's amazing that we think that my architecture can be emergent. How can you hopefully, in you moving like blindly in one direction, you're going to stumble upon the perfect architecture? Maybe you could get lucky, of course. So there is this principle from Agile, of course, the best architectures, requirements, and designs emerge from self-organizing teams. Agree to a certain point, but if you fully follow that, then you have only the matter of emergent architecture. And that's optimizing the parts again. So it's very hard to predict this beforehand. By being emergent, you have to sort of be open for refactoring, even huge rewrites if you create code with this. So, and also we remember with the biases that I said earlier about the germane cognitive load. We tend to like to box things, as we said. That's what we do when we do modularity. But we also like to box things in a weird way. Oh, this is the 90s. Now people looked like they was acting like this in the 90s. Oh, you use such a Gemini. Right? We like to box things because it makes life easier. It's less complex. And also think when we do OO, we end up, this is a customer class. Of course, we're going to have a customer service. We have a product class. Of course, we have kind of product service. We looked at the entity. So we have there's a bias to us there. So I think we need something that can correct this. I'm not saying again, as Eikhoff said, analysis is not redundant, but we have to support it with something else. So that is when I think we need something. It looks like it's top-down, so maybe on illustrate more like this. It's more like outside-in. Again, what Eikhoff said, take one level up. You do synthesis. Understand what is affecting the thing that you're looking at. So do both. So how do you do then this top-down, outside-in thing? I haven't got time to go through the techniques. This is where I have to shave this presentation today, but I can mention a few that I like. So it's a bit biased, but I like the idea when you were in a commercial setting in a company, you want to understand the business capabilities that this company is sort of building and going to the market with. So you understand the business basically, the business model, the business architecture. So a business capability is a particular ability or a capacity that a business may possess or change to achieve a specific purpose or outcome. Nice that they use purpose there, accidentally, by the way. So then you get these purpose, social systems, whole thing again. Just an illustration of what such a business capability map may look like. There's a technique for this. So this could be an enterprise. There's some corporate management. There's some product development, delivery, and et cetera, et cetera. And also this is nested hierarchy, so you get another level here as well. You do market development. There is the contract management, the direct marketing, market analysis, and so on and so on. So if you use this, not as a pattern for how to do modularity, but if you get inspired by it, at least, then you have some anchoring in a bigger system. And also, these are fairly stable. They don't change unless the business change. So you don't have to worry about things changing willy-nilly. And this stuff only changes when the business decides to do a change, a pivot or whatever. Right? So it's a good, sensible default, I find. Look into it. Let's go. And then, of course, we have domain-driven design, which has a lot of focus on this. They also do this synthesis thing. This is one of the good things that came out of COVID, by the way. There was a bunch of people who got bored at home. They said, "Oh, can't we just give some patterns to people that they can know, or some process things that people can look at to get faster into what domain-driven design is?" So the DDD crew created, for example, this design starter model. This is very linear. 1, 2, 3, 4, 5, 6, 8. So they decided to create this instead later on. So it's more, there's like iterations there and feedbacks and all cool stuff. But I like this, it illustrates the thing anyway. So you have first, align, understand the business model and the business needs. Then you look into what the boundaries are. So you have to do this first before you move to this one. Of course you will iterate, but you would definitely do this first. Give some idea of this first. And then you decompose it and connect it, end up in code at 8 there. And a good way to do this discovery part and the decompose part is event storming. It's a brilliant technique. He's with Alberto Brandolini himself, the inventor of event storming. Because when you do this creating this long story, like a value, like a process map even looks like that, but using stickies and events instead of BPNM that maybe others use. And you end up with something that looks like this on the wall. And then you can see there are groupings of stickies. And they can be indicative of domains, as they call it, or subdomains, and bounded context, as the term that they use for implementation in domain design. Again, this is again doing synthesis, right? You go up before you go down. An interesting thing, just a side note there, an interesting thing that I sort of came across when I started looking into social technical system design specifically, there is something called context mapping in domain design. Who knows domain design a little bit? A few hands. So these are about how bounded contexts interact with each other. How can they interact? What's the communication lines between them? You have some examples here. You have something they called partnership. This means that this context and this context is very tightly coupled because they are in partnership. They are in contact constantly. And then up here you have an ACL, anti-corruption layer. So you and there is no contact. Actually, you basically want to you want to map everything that comes from here. You don't trust anything that comes from here into here. You don't want this one to corrupt this one, basically. And then you have the conformers to saying, oh, we believe everything you do, we're just going to do the same. We're just going to copy it. So you see, when you look at these patterns, for me, initially when I started doing domain design, these were very technical for me. Right? This is how you write code, and there's a publisher subscriber thing, and there's like the ACL, as I mentioned, open host APIs and all that stuff. But it's actually just as much as social technical patterns. It's about how teams cooperate. So if you have a team where you have the need to put in an ACL, that's a pretty negative pattern to have. So you just see that there are a lot of social aspects to these things. Often you need them, though. That should be said. If you're interested in any of these techniques I mentioned, and there's a loads more, I recommend this book. Free. There was also something I think Kenny mentioned it in the previous talk. On the InPub, you can of course pay for it and give money to charity, but it's basically free. There are a lot of other interesting techniques there. Yes. So let's sort of try to wrap this up a little bit. So the goal is we want to have teams that are semi-autonomous. I never say autonomous, and I'm probably going to stop using autonomous altogether because it's confusing. And we said semi in front of it, people forget semi and just think autonomous. So actually in social sciences, they stopped using the word. The branch I'm reading. They're using self-managing team instead. That's the core bit of it. Not them being autonomous. That's one characteristic or intrinsic motivation that people have, but it's not the only one. So you want to have this self-managing team, but again, how do you manage this then? If you look back at the sort of the modularity I showed earlier, how does this look like? They need to own their own data. They need to own their own tools. That includes process for doing whatever they do in a team, Scrum, whatever, like the processes as well. They decide themselves that they are self-managing. There's nothing like somewhat self-managing. They are self-managing. They decide themselves. They all have to do that themselves, by the way. And by doing this, they have a sort of their turf. This is where I belong. This is where we belong. That's what we own. We interact with these people because we have to and we like to or whatever. That's our reasons. But they want to be as self-managing as possible. So I think, back to what I said about emergent. I think, yes, emergent can work. If you're in a fairly trivial domain, sure. But if it's something that looks like complexity, I have no belief in that emergent can work. You're going to run into problems immediately. So I used this illustration. I used this before to illustrate what can happen if you do microservices wrong. I've been part of, we're going to microservice this, or we're going to, I was actually so them, but we're going to split this monolith into pieces, right? So we started picking the low-hanging fruits. Billing, that's easy. For this was a telecom, so sending SIM cards is easy. But then you're stuck with what's hard. What's the rest then? They didn't get any further than that, so they still have a huge chunk still. Because it's so hard, because if you do start to pick things apart randomly like that, you're going to end up with a distributed monolith. So I think it's really dangerous to do only lean on emergence. So I think, again, you remember I mentioned earlier that the central part of system thinking, or complexity specifically, is about multiple perspectives. So I mentioned a few techniques earlier. The idea there is both business capability mapping and especially brainstorming and like domain design is getting the whole system into the room. You don't exclude anyone. Anyone who has a say in it should be in there. Discuss it together. So the elephant illustration is really good there. They all have different perspectives on things, and that's how you deal with, at least one of the better ways to deal with complexity. So I think somewhat similar to what Rebecca and I, mentioned earlier, is that these what did she call it? The architecture ideas, that sort of the ways functions. Yeah, yes, fitness function. Thank you. So it's similar to that. You need to have an idea of what good looks like. You don't have to define in details, but have an idea instead of that broken window pane, the glass. What about this thing? Have an idea where you want to put things. Then you do emergence because you haven't created it from scratch, but you have an idea where things are going to happen. You have an idea where the red one is going, for example. Then you can also stray for the path, and that's really good when a lot of good advantageous things when thinking like this. So analysis yields knowledge, synthesis yields understanding. Yeah, sorry. Yes, and with that, I'm gonna wrap up and say this. I want us to leave the machine age. That's the core message. Let's move into the system age and look at the multiple perspectives that we can get. Thank you.
We don't have time for questions, but we have one question I would like the answer for, so I'm going to bend the rules. Whatever got you into systems thinking?
Sorry?
What got you into systems thinking?
I think that was actually when I was doing domain-driven design. Somebody tipped me off about Donald Meadows. So I think actually thinking a system book was the first thing that kicked it off for me. And then, of course, you can read that and put it away and say, okay, nice and well and all that. And then I came across this sociotechnical system term, which sounded very interesting. It had system in it. Okay, I knew a little bit about systems. Social tackling, what on earth is that? And it proved later on that the guy who coined the term social technical architecture, which definitely comes from domain-driven design, he didn't use the original definition of what it was. So when I started digging, I actually ended up in a wrong area than he thought of it. But then you got into social sciences. And then you got into the open system and all that. So it blew up. It's a huge rabbit hole to get into, I must admit. But yeah.
Thank you again. Let's give him another hand.
Thank you.